Hey everybody. So we're going to talk about lenses today. Alright, and I've got two lenses here. This one is a concave lens, this one is a convex lens. And you might notice, let's see if I put this one in front of here, you might notice, what I want you to notice is that everything gets smaller up on my head in the front of it, and my head gets smaller and smaller no matter where the lens is. I pull the lens really far away from you and it still produces a small image, and notice that my head is upright the whole time. I'm never upside down. As opposed to something like this, this is a convex lens. It's harder to see, but you might be able to see my eye there. Notice my image is now upside down. So see, there's my nose, there's the mouth. Produces an upside down image when it's far away, but when you get closer, notice things get really big, right? So this is also your magnifying glass. Convex lenses is what we use for magnifying glasses. Let's do this and look at something else far away so you can tell what's going on. So there we are. Everything is upside down now. There's your door upside down. All right, so those are your two types of lenses we're going to talk about today. All right, to start off with, we're going to talk about convex lens first. The convex lens is also called a converging lens. You need to write that down in your notes on lenses, which you should have in front of you while you watch this video. A convex lens converges light, and you need to draw this diagram, and the diagram you have in your notes there to the right of where you're writing. With a convex lens, the light rays come in from the left side of the lens, parallel to each other in this case, because the object would be very far away. Come in parallel to each other, and they get refracted through the lens. Notice that now we're dealing with refraction, not reflection anymore. Refraction happens, and these light rays converge at the focal point. Remember that the solid rays are real rays, and the dotted lines are virtual rays. Sorry about the bells. So the dotted lines are virtual rays. The reason why we put those there, remember, is that at this point the light bends because of refraction. And remember that from before, we know refraction is when light speeds up or slows down because of a change in the medium. So this would be a glass or plastic lens. When the light goes into that lens, it changes speed, and when it changes speed, it bends. In this case, it's slowing down and bending toward the normal, actually doing it twice, and we'll draw a diagram of that in just a minute. Point is, your eye or your brain doesn't know about this refraction bit, and so you can imagine that your brain sort of thinks that the light came in a straight line from somewhere back here. That's why we trace the virtual ray. So convex lenses converges light, and convex lenses have a positive focal point. And it's very important that you understand what a positive focus means. With a mirror, it was different. With a mirror, positive focus meant that the focus was in front of the mirror, on the same side as the object. Positive focus is just opposite for a lens. For a lens, you need to write down that it means that the focus is on the opposite side of the lens. So for this convex lens, the object would be somewhere over here on the left side of the lens. That's where the light is coming from. And the focus of the lens is on the right side. Realize that in this particular class, all of our objects are over here. That's the way we draw ray diagrams. But obviously in real life, we can flip it. We can put the object over here, and if that's the case, the focus would be on this side. The point is that it's just on the opposite side of the lens compared to the object itself. Examples of these are magnifying glasses. Magnifying glass that we talked about. Anything that magnifies something, like a telescope or a microscope or binoculars. Any of those things use convex lenses. Another example of a convex lens is what you see here on the screen, because the convex lens is created, this image on the screen is created by, if you can see it, there's a convex lens in the projector. And so I'm going to leave this on the screen, and I want to show you something. So I'm now here at the projector, and you'll notice that the image on the screen begins to change. And it's probably making the camera go haywire. All I'm doing is I'm changing the focus on the projector. You'll notice that the image changes, it gets very blurry. For some of you, you see this type of image early in the morning when you first wake up before you put on your glasses and contacts, if you wear glasses or contacts. But now the light is focused. So all that was happening there is within this projector, we have a convex lens here that projects that image onto the screen. And all I was doing is, by changing the focus, I was moving this lens forward and backward. And what that was doing is it was changing where the focal point was. It was moving this focal point forward and backward. And you only get a clear image on the screen if the focal point is directly exactly where the screen is. If the focal point is back here or in front, we get a blurry image. Another example of a convex lens that is most important to all of you is your eye. All right, and if you're nearsighted, you might know why you are, but if you're not, here's a decent explanation of it, short explanation. So if this is your eye, like this, remember that there's actually an iris here in the front. That's where we let light in. Behind your iris is a convex lens. Now this convex lens isn't made of glass like the ones that we've been dealing with in class. This convex lens is a proteinaceous lens. It's made of protein. And what happens is light comes into your lens, and the lens, this is a converging lens, so it converges the light, ideally, to where it falls at a point at the back of your retina. This is where you have all your rod and cone cells back here. They sense the light, they sense an image, and they send that image to your brain so that you can see. So that's the way that works. However, if you're nearsighted, what actually is going on is that your eyeball has a funky shape. And your eyeball could be shaped something like this, and I think farsighted actually is like this, and this is nearsighted. Regardless, the point is this. At this point, the rays actually cross each other. They cross like this. They continue past each other. And that means a couple of things. Number one, the image that falls on the back of your retina is actually upside down. These lenses form real images, and the images is upside down. And the image that I just showed you on the screen actually is an upside down image. It's inverted because the image is sent into the lens upside down, so that when it inverts, it's right side up and we can read it. But the image that falls on our brain is on the back of your retina rather, is upside down, and it gets sent to your brain, and your brain flips it so that you can see everything right side up. But the other point, the other consequence of that is that if your retina is here or it's here, notice that at those 2 points the light rays fall on your retina, but the light rays have not come together. They're not focused. Just the same here. If we put the screen here, or let's make the rays continue to go this way. If we put the screen here, in either of these cases the light rays have not come together, and we get a blurry image. And that is why you see a blurry image if you are near or far sighted. And the way that you actually focus your eye is there's actually some muscles attached to your lens here, and that can compress or stretch the lens, and what it does is it actually changes, it can possibly change the curvature of the lens. The curvature of the lens can change the focus, so you can focus on things far away and close up, but if you're near or far sighted, your eye is shaped so differently that you actually cannot compress your lens enough to accommodate for different distances. So the eyeball, the lens in your eyeball is one of the most important examples of a convex lens to each of you. There's also a video linked on this page called the arrow trick video that shows you another example of actually a beaker of water being used as a convex lens, and it's flipping the image of the arrows that you see. So make sure and go and look at that video. We spend a lot of time on convex lenses because we use them more than we do concave lenses, but you need to know that a concave lens is also called a diverging lens. You might want to write that down, because it diverges light. The light rays come into the lens the same way as they did to the convex lens, but instead of coming down toward the focus, they go away from each other. The real rays diverge away from each other. And then of course, remember, we've got virtual rays. The virtual rays are what are going to come together back here and form a virtual image we're going to see. Concave lenses have negative foci, negative focal point. Remember, with a convex lens, positive focus meant that the object was here and the focus was on the opposite side. With a convex lens, object is here and the focus is on the same side, right? So if the object is on the left, the focus is on the left. If the object is on the right, the focus is also on the right side, right? And again, as I said, these guys always form a virtual image. It's a diverging lens. The real rays always diverge away from each other. They will never come back together, so it's impossible to form actually a real image. All right, so let's start looking at ray diagrams. Remember that we draw ray diagrams in order to find where the object is and whether it's real or virtual, up and it's flipped or upright, all that kind of stuff. We did the same thing for mirrors, and remember with the mirrors we had 3 principal rays that we drew and we only needed 2 of them, and that's the same for this one. The 3 rays that we're going to draw are going to sound similar to the ones we use with mirrors, but they're not exactly the same. So ray number 1 is exactly the same. Ray number 1 starts at the tip and it starts horizontally parallel to the principal axis towards the lens, and then it gets refracted through the focus. Now it's really important at this point to know where the focus is, to know that this is a convex lens. It has a positive focus, therefore the focus is on the opposite side from the object. And at this point on your notes, again, it should be obvious you're on the image of a convex lens, which looks like this. And remember, this is a refraction point, and so we always get a virtual ray behind the refracted ray because this is what your mind thinks is happening. So ray number 1 goes parallel and is refracted through the focus. Now let me stop right here, and I want to explain this refraction part and why the ray of light actually does this. So on that lens that looked like this, we had light coming in and it refracted this way. I just want to take this one part right here and blow it up much larger than normal. And so we have, and it's kind of exaggerated image, but we have one surface here, the other surface would be here, right? Because we can imagine the rest of the lens does something like this. Light ray comes into the lens. When that happens, as the light goes from air into the glass or the plastic, hopefully you can realize that the light's going to slow down. And we need to remember that when light slows down, it refracts, it bends toward the normal. So we can draw our normal. It would be something like this, perpendicular to the surface. So instead of moving in a straight line, we're going to bend toward that normal line, something like this. All right, that's our first refraction point. The second refraction point at this surface, now we're moving from the glass back into the air. Realize when we go back into the air, the light's going to speed back up again. So here's our normal, and when light speeds up, it's going to bend away from the normal. So again, instead of moving in this straight line, it's going to bend away from the normal. So there we go. So there's your 2 refraction points that you have, and that's how we get this single refraction that we do here. We only draw a single refraction point because it's easier, and that's the basic effect of all this is this light comes in, we make believe like it comes in here, and then it gets refracted that way. That's the way we draw it. Alright, so that's ray number 1, parallel and through the focus. On the same diagram, we're going to draw ray number 2. Ray number 2 is kind of like the first one, but not exactly. It's a little bit opposite. Ray number 2 starts at the tip and goes through the opposite focus. This is the focus of the lens on the opposite side of the object. Now we're going to go through the opposite focus. That's the one on the same side of the object to the lens, and this one gets refracted horizontally. And don't forget the virtual ray behind the lens. So the ray number 1 was parallel and through the focus. You should have that one. Ray number 2 is through the opposite focus and gets refracted parallel. Right now these 2 rays on your paper should be intersecting right about here if you drew them correctly. Ray number 3 is really simple now. Ray number 3 goes right through the middle of the lens, and it actually is a refracted ray. That may look kind of strange to you, so we are going to put a virtual ray back here beside it. Let me explain what's going on with ray number 3. With ray number 3, what is happening is we're getting a ray of light that's coming into the lens above the principal axis, and it's leaving the lens below the principal axis. We draw it as a straight line, but you need to know it's not actually a straight line, because at these 2 points we have 2 surfaces that are basically parallel to each other, just exactly like the 2 surfaces that you sent the laser through in the refraction lab. Those 2 surfaces were also parallel to each other. So these were parallel, which means their normals were parallel. And what the effect of that was that this ray and this ray, I didn't draw it exactly right, but they're parallel to each other. So all the ray does is it just moves over a little bit, is all it really did. And so when your eye sees this one, we can trace this virtual ray back here because that's where it quote unquote thinks it came from. In a lens, we're going to go ahead and draw that as a straight line because it simply just moves over just a slight bit. With a thin lens, that's not very much, it's very negligible, but we need to realize it is a refracted ray, so we do draw the virtual ray coming back behind like that. So it is refracted just a little bit. So the end result of this, you should have an image that looks like this. It gives us a real image because the real ray is crossed, the image is inverted, and it happens to be magnified in this case.